Good morning. Here we are once again at the physics video lecture. It's physics 105A video lecture 23. Okay, we want to talk about Fourier series, but I'm going back to some review of the small oscillations material. Got that test coming up and had an interesting question from one of our colleagues. So once more with feeling, and I'm going to try to do a split boards thing because we have a couple of different techniques for the whole Newton's law small oscillations business. So here's what we're going to do. Let me remind us, since this is review, we can actually work our way through it systematically and get some overview here. So we're solving Newton's law, one dimension, with forces that are just a function of position, okay? And we do all kinds of techniques. One thing we do is we learn to define the potential energy minus the integral x prime dx prime. Make sure you realize the prime is just an integration variable. It means nothing. Beyond that, the argument is up here. But we have this relation that our force is just minus the derivative of the potential energy, okay, with minus u prime of x is the force there. Good. So when it comes to solving Newton's law here to, discover the relation between the motion and the force, we have a couple of methods. And that's what I want to set up in two columns here. Yeah, let's just go ahead and do it this way. We have the quadrature. Okay, so I'm going to continue with this again a bit. So this, of course, is fundamental. But what we did when we discovered this property here, we found that, so we find that 1/2 m x dot squared plus u of x is equal to the constant energy, and we use that to learn how to solve, in principle, this differential equation, because after all, this is now a first order differential equation. We started with a second order differential equation. Okay, so I'll say then what happens. Then we have t is equal to dx prime root 2 over m e minus u of x. This was our fundamental solution method, and now we have t of x, and if we're able to invert this, do the integral, invert it, and get x of t, then we're done. Okay, so in a sense, this is the solution to the mechanical problem. Okay. Continuing, and also we had potential energies with a local minimum. Also, if u of x has a local minimum, then what? Well, then we have oscillations, and under circumstances, harmonic oscillations, under particular circumstances. U of s has a local minimum, then oscillations. And if there's a local minimum and we do small oscillations, then we got the harmonic oscillations. We got them completely out of this formalism, okay? The cosine, omega t, etc. And oscillation, I'm going to write oscillations, etc. So we did all of that without going back to Newton's law in this form. So what I want to do is compare two methods, because we've done so much. This is, by the way, this is just such fundamental material that carries on into your entire physics career, okay? So it's always worth talking about this. And in particular, this local minimum business here is so important. Okay, so here's what I'm going to do. I think this will fit on this board now. Let's have our, so next, put this on this board if I can. Small oscillations, okay? Okay, so here's what we're setting up. Two columns here, one with Newton's law, and one with Newton's law as well. But what are we going to have on the right side here? We're going to have minus u prime of x, okay? Because by definition, that's exactly what that is. So equals minus u prime of x. And I'm going to write it as a derivative. It means the same thing, of course. Okay, so those are identical and the same. And this is the one we've worked with. So now, so next, if u of x has a minimum, local minimum at x0, we have u of x can be expanded, u of x0, u prime of x0, 1/2 u double prime x minus x0 squared. Okay. And since it has a minimum at x0, this one here is just gone, equals 0. And of course, this is a constant. So what do we have here? In fact, I'll even do a next step, u of this, and minus d dx of u of x is equal to, derivative of a constant is 0, at 0 plays no role as well, so it's minus d dx of, let's put a bracket around here, 1/2 u double prime of x0, x minus x0 squared. You know, it goes on here, but we're not having that discussion right now, okay, with small oscillations. So we ended at that part of our Taylor series. Okay. So this is where people sometimes get a little confused. This 1/2 u second derivative, this is a, 1/2 is of course a constant. That second derivative evaluated at x0 is a constant. So when I take the derivative of this thing, and I've got my minus sign as well, minus is just 2 cancels the 1/2, this is the constant, x minus x0, that's it. So I end up with u double prime of x0, x minus x0, right? And we'll ignore what's downstream there. So now let's set up this equation here. Now we have what do we have? mx rooted equals minus okay. So far so good. It's not all going to fit on two board. I'm going to send it up in a race. But let's do the left side here now. Okay. The left side, we're talking about small oscillations. So of course we can also expand f of x in a Taylor series. And let's do that. So yeah, next, on this side, expand f of x around x0. So we have f of x is equal to f of x0, f prime of x0, x minus x0. I'm going to take one more as well. So f second derivative, x0 squared over 2. So that's our expansion of f of x, and for small oscillations, we could go ahead and plug that in on the right side as well. I'm going to do that. But I'll note here, f of x0 is a constant. F prime of x0 linear quadratic terms. So I have to relate that to the small oscillations problem. So what we have here, since f of x0, let's just write it out first. Okay. F of x0 is equal to, going back over to the other side here, minus u prime of x0 equal to 0. So over here it was a local minimum of the potential energy. Here it is what? An equilibrium point. Okay. So f of x0 is 0. I'll go ahead and strike this. And since we're doing, you get these two terms, this second derivative part for small x minus x0 is much, much smaller. Okay. So this is literally 0. This, we're just going to say small. Okay. This corresponds to the terms that we didn't even write down up here. So now we can fill in our differential equation. M, two derivatives, equals f prime of x0, x minus x0. And we'll leave everything off there, okay? Let me do one more step, because this is called, let's even write this down. This is, we'll name it star. This is what's referred to as the linearization. Okay. This is the linearization. Of that function. In fact, this reminds us of when we were discussing Taylor expansions on general principles, right? We had a constant, didn't matter if it's 0 or not. This would be the line tangent, the straight line tangent to f, at x0, point slope formula. This one we discard here. So that's the linearization. Now, the relation to this equation here is the following. I'm going to write minus, and then I'll just parentheses negative f prime of x0, x minus x0. So this here, because of our relations between the force and the potential. See, one derivative here, two derivatives here. These equations are identical. If I pull out the minus sign, it's because I'm actually at a local minimum. Okay. Pull out the minus sign, I'm at a local minimum. So let's continue with this now. The point here is when you linearize your differential equation, your Newton's law, you linearize that force, you're doing exactly the same thing as when you expand your potential energy to quadratic terms. Okay, these equations are identical. This, in a sense, is more general because you don't have to be at a local minimum. When we're doing small oscillations, we're focusing on the situation where there is a local minimum. Okay, so here this would just be the linearization. It's a little more general. This is more transparent because once you can figure out your potential energy and graph it, you kind of have the situation in front of you. It's a function. Does it have a local minimum? If so, then keep working on it. Okay, let me just remind you of the solution for both of these. I'll put it right between them. Now let C equal x minus x0. That's the small quantity. Put that in parentheses. Small quantity. How small? Small enough. Okay, for small oscillations. If that's the case, we trivially have two time derivatives. The same, because that's a constant. And over here we have mc second derivative x0. And over here we have minus u double prime of x0 times c. Okay. Now, it's kind of awkward to have a minus of a minus, but it's important to make that point there. Okay, that's the identity between those two. And of course, this here minus omega naught squared c omega naught squared is equal to u double prime of x0 divided by m. Okay. And the exact same thing holds true right here. Minus omega naught minus f prime of x0 over m. This, of course, is a positive quantity. Okay. So yeah, the linearization, this is such an important technique. And when we did our expansion, that's what we were doing the whole time. So at the risk of making things more complicated, but I hope I didn't, both of these lead to this differential equation. And as soon as we have something of this form, two derivatives minus a constant times the quantity itself, that is our equation for harmonic oscillations. Okay. And if we go back to our definition, a cosine omega naught t plus alpha, we're done. Holds true for both sides. So yes, you can do a linearization directly from the force, or you can construct your potential energy first. And we'll see next semester the general, the more advanced theory of dynamics. We spend considerable time always constructing energies. Okay, we don't see that now that's the most general method is to put together your energy expressions. We'll do that next semester. Right now, these are both equally valid and useful. Okay, same solution over here once you get to that differential equation. Can't be stressed too much. As linearization, it continues on in the higher dimensions. So instead of one variable, n variables, it continues on into different types of objects as well. In all manner of physics, field theories, etc. You're locating some kind of local equilibriums, kind of local minimum, and expanding your energy expressions. Good. Let's see, have a look at the clock. Okay, fantastic. You know, I may even continue this example. Why not? Let's return to this example of a potential energy function that I had given in an earlier lecture. It's one that we're going to encounter later on in the semester again, so it's a good one. So, example for both of these techniques. U of x is equal to a over x squared minus b over x. And this is a dynamics where a and b are positive and x is also positive. Okay. When we study gravity, central force problems, this is the most famous, important potential. It comes about in an interesting way. But for now, it's just a nice formal object to work with. And we can go ahead and graph it as we did before. And this technique is also, this is a good review. I have something similar like this for you guys next week. So what you do is you look at this function in the limit of small x, and then that 1 over x squared dominates, and it just does what you think it does, okay? It goes like that. But in the limit of large x, this negative b divided by x dominates. Okay, so for large x, this one dominates, and actually, nothing wrong with repeating ourselves. Let's do this. So here's our 1 over x squared. Here's our minus 1 over x. Okay, you can't really tell which dominates just from graphing them here, but then you check the limiting behaviors. This one's going to dominate for small x, this is going to dominate for large x. Therefore, the graph is something like this. Comes under the axis. So there, once you succeed in graphing that, you see very clearly there's a local minimum there. We can do a small oscillations problem. Okay. You know, I could have, instead of minus b over x, I could have, you know, plus b times x squared. Okay. Then the same thing would hold true. If it were b times x squared, you know, we get something, we get a big U-shaped thing here. Again, it would have a local minimum. Okay. So from here, so I'll just write next. U prime of x0 equals 0, and omega squared equals u double prime of x0 divided by m. Right? Now we have the theory of that. We can do that. Make sure we write our 2 primes there. We can do that. So you don't have to do all the intermediate steps. We've studied that repeatedly, so we know what happens. So there's our 2 squared. On the other hand, this is also an interesting object to go ahead and find the force. Okay? So since u of x, what is the force? What is the force? Question mark. Well, f of x equals minus u prime of x. So minus, and what do we have? A x to the minus 2, so minus a minus 2 x to the minus 3. And then plus b. So that's bx to the minus 1. So plus b x, oops, x to minus 2. So b over x squared. Actually, did I get the minus sign there? What's more feeling? So minus a minus 2 over x cubed minus negative b over x. So yeah, I had the sign mixed up there. So there's the minus sign from there. B minus b minus 1 x squared. Okay. So 2a over x cubed minus b over x squared. So there's our force. And the same thing, so the same process where I take the derivative, this thing vanishes at x0, okay, and then take the next derivative to get omega squared. For this function, this already is the derivative of this, so I have to find x where this vanishes, and then I have to expand f of x, or take the derivative of f, so f prime, to get the frequency. Okay. So they both work, and you know that would be the process up there to do the linearization. The method with the potential energy has the advantage of being very transparent as to what's going on here, because you know when you're at a local minimum, you've got some oscillations in there. A function like this, it's harder to analyze for what's going on there, but of course it can be done. Okay, so now I'll check the clock again. And we'll move on to our Fourier integration. I'm having trouble getting off the ground with that. Okay. Actually, while I'm on the subject here, if we're analyzing this force function, we have a similar analysis to what we had here. When x is small, this term dominates and the force is positive. Okay. That means that's because it's pushing it away from that local minimum. Okay. When x is large, the force is negative, and it's a restoring force, in other words. It's pulling it towards that local minimum. So we have that here as well. Okay, now let's move on to the Fourier integration. I think we have time to do one of these. So returning to Fourier series. We've set this up a couple times now. So what I'm going to do is remind us we were going to expand this function here. So what are we looking at? X, 1, 2, 3, pi, 1 minus 1. We were looking at this function here. Minus pi. So this was 1, this was minus 1. Okay. This function here. And what happens in the middle? Well, actually goes through that point. but we'll just say f of x equals -1 for minus pi less than x less than 0, +1 for 0 less than x less than pi. And what else do we know? We're going to try expand this in that Fourier series, which was the sum c sub k e to the I kx over all integers. So k goes from -infinity to +infinity. And we had, for these c sub k's, 1 over 2 pi integral minus pi to pi f of x e to the minus I kx dx. So we're just going to go through with this program and see what happens. Okay. This is definitely a function for which the Taylor series is not useful. Okay, it's kind of a step function. Okay, here we go. So we're going to try to get the general c sub k right out of our definition, 1 over 2 pi. Now we can break this integration up into the left half and the right half. So we're going to integrate from minus pi to 0, where our function is equal to -1 e to the minus I kx dx. And then the right half will be 1 over 2 pi, 0 to pi, +1 e to the minus I kx dx. So we just have to do these integrals and not get lost in all the signs. Okay, so we have -1 over 2 pi. The integral here is 1 over minus I k e to the minus I kx. Can evaluate minus pi to 0. And here we have +1. We have 1 over minus I k minus I kx 0 pi. Okay. So what do we have here? We'll keep the I in the denominator, but we can get rid of these two minus signs. We have 1 over 2 pi. Then we evaluate 1 over 2 pi I k. Then we evaluate at 0, that's a 1. 1 minus e to the minus I k negative pi, so that's just a plus I k pi. And then we have plus 1 over 2 pi, 1 over minus I k e to the minus I k pi. Upper boundary -1, 0, negative boundary. Okay, so that looks kind of involved. Okay, but remember we were talking about e to the I pi, or e to the minus I pi. So this thing right here is just going to alternate between plus and -1. Okay. So when k is equal to 0, it's equal to 1. When k is equal to 2, it's equal to 1. and so forth. When k is equal to 1, it's equal to -1. Then we get -1 minus 1 is 2. So this expression in parentheses is going to alternate between zeros and 2's depending upon which power of k, if you have even or odd k. So I'll put a note here. And by the way, with ik pi or minus ik pi, it doesn't matter. Okay, let's go ahead and write this out. E to the ik pi is equal to cosine k pi plus I sine k times pi. Okay, so these are all 0. Right? Okay, sine of k times pi, 0. So what does this equal? Equals -1 if k equals plus minus 1 plus minus 3 plus minus 5. Okay. And it equals +1, so +1 k equals 0 plus minus 2 plus minus 4, etc. So that allows us to evaluate these. So in fact, our k goes from minus infinity to plus infinity only has the odd numbers, because when it equals +1, both of these vanish. Okay, so I'll put that under here as well. Equals -2 k equals odd and equals 0 for k equals even. Same thing over here. So now we're just going to have the odd integers I may leave this for you guys. This is actually a good place. I want to give you a couple more tips though. A couple more hints. Let me check that. Consult the clock. There's another important point to make here. So yeah, we can pull this together pretty quickly now. Okay, we're gonna have a 1/2 pi. We've got ik. In fact, you even see the 1 minus here and this -1. So we can actually get rid of one of these minus signs here. So we can pull these together. Okay. So if I factor out a -1, I have identical 1/2 pi ik. 2 pi ik. Maybe I'll go ahead and do that. Equals 1/2 pi ik times 1 minus e to the I k pi. Anything else? Times 2. We get 2 of those, right? 1 minus it. Get rid of that I there. So we get 2 of these. I don't need this extra bracket here. 2 minus e to the I k pi. And since this is just this alternating way of now writing either 2 or 0, depending if they're even or odd. So now I want to look at one more thing up here. That's something I could have drawn our attention to before. And that has to do with the structure of these things here. It turns out that C sub negative k, like C sub minus 2, is equal to C sub k complex conjugate. I'll let me write that. So C sub negative k is equal to C sub k complex conjugate. Because if I plug in minus k here, here. If I plug in a minus k, this is like replacing I with minus I, which is what turns this thing into its complex conjugate. So C sub negative k is C sub k star, so that these things actually appear pairwise. So we're looking at C sub k e to the I kx plus C sub negative k e to the negative I kx. These things show up pairwise and can be evaluated pairwise. What's going to happen, because I'm going to end this right here, and possibly leave it for you guys, or maybe complete the problem later. It would be a good one for you guys to work out to completion. What's going to happen is you're going to end up with a sum of signs. Okay, with the odd powers, they're just going to be signs. And the same thing's going to happen on this. It's going to happen on this level. Your C sub k e to the I kx plus C sub negative k e to the minus I kx is going to turn into a sine function. And so the result of the whole thing is going to be real. Okay, so this is complex. The result is going to be a summation of sines. I think I'm going to leave it right here. Should I write this down as a homework? I'll pick up with this next time and decide how much of it is homework. We could possibly complete it here at the board. At any rate, it's a good one. You can see where it's headed now. All the pieces are in place. If you actually sum this up, you're going to just get a sum of sine functions. And okay, let's leave it at that. Let's check the clock once more, but I think our hour is up for today. Yeah. So there you have it. We're not done with this because we spent all this time on that other interesting stuff, but we're gonna finish this one, and then I'll give you some assignments of this material. Okay, good. See you guys next time.